So I've actually only been doing machine learning as a job for about 6 months, but I feel in that time I've learned a lot about different pitfalls that you can run into, and I've also learned more philosophically what machine learning really is and how it relates to other areas of science and engineering and things like that. So that's what kind of motivated this talk. So I'm going to go through a bunch of pitfalls. Some of them I'm going to go through fast. Some of them I'm going to spend more time on. One of the ones that I'm sure a lot of you who do this are aware of is overfitting. So this is kind of a tongue-in-cheek depiction of it, but this is actually fairly accurate depiction of overfitting. Overfitting is when you have a model that is fitting noise in your data. The classic example of this is if you have some function and with noise, then an example of a model that you could fit that has varying degrees of complexity is to try to fit different polynomial functions. So you start off with a straight line, y equals x, and x plus b. Then you could go to a fourth degree polynomial. But then if you go too high, your model is going to fit the data really well, but it's not going to interpolate between the points to that well because it's fitting noise in the data. And that's the problem with overfitting. So the way you check for overfitting is you take some of your data out and you pull that out. And that's called the test set. And you don't include that in your training. And then you train your model, fit your model, and you look at the performance in the test data, so the data that you didn't train. If the performance of the model in the test data is really good, the training data is really good, but then when you go to the test data, it's really poor, that's a sign of overfitting. So, again, we will look at the gap between performance in the training data and performance in the test data, and we want that gap to be as small as possible. The ways that you can decrease overfitting are regularization. I'm not going to go into what that is, but it's most machine learning models have a regularization parameter you can tune to kind of reduce the complexity of the model and avoid overfitting. Or you can change the structure of the model, which would be hyperparameters. So you always want to show your, and also when you report the results of to say in a journal article or even just to other people in your field, you should always include the accuracy of your model in the training data and the accuracy in the test data, not just the test data accuracy. So that way people can see that you do not have overfitting. So I'm just going to move right along to some of the more kind of interesting, more fun stories here. And a lot of them have to do with bias. And the term bias has several different meanings in machine learning. One meaning of the word comes from statistics. And in statistics, when you're doing regression, fitting a model to data, the error in your model can be broken into several parts. It can be broken into bias, variance, and then irreducible error. So bias is, in statistics, has kind of a technical term, meaning a technical definition, meaning error which is coming from the fact your model is not a real, true representation of the data. So it's error that's coming from the model itself. So that's one meaning of the term. Another area where the term bias comes up is when you have biased training data. So I'm going to give some examples of that, but this comes up a lot in elections, polling, for instance. If you just use landline phones, then you're not going to get a representative sample of all of the eligible voters, because people who answer landline phones tend to be older. They tend to live in different certain areas, things like that. So that's an example of biased training data. And then there's what I'm calling social bias, or sometimes called discrimination, which is when the machine learning system is doing things we don't want it to do, so things that are against our values. And the last two are closely related in practice. So as an example of biased training data, there's a famous story that's told a lot called the tank story. And in this story, it's alleged that in the 1960s, the US government was trying to, they had funded some researchers to build a machine learning system that could detect whether there was a tank present in a photograph. So they trained up their system on several hundred photographs. Some of them had tanks and some of them did not have tanks. And they also held some of those photographs out and further to test the model. So they were testing the model, and they found they were getting really high accuracy. They were getting 98% classification accuracy. But then they brought in some new photos that were not part of the original set. And all of a sudden, the machine learning wasn't working at all. It was doing worse than chance. And what they discovered was that all the pictures that had tanks in them were taken in sunny weather, and the other pictures were all cloudy weather. So really, what the machine learning system was learning was whether the weather was sunny or cloudy. And this story is given as an example of how bias in your data can often mislead your model. Now, there's a kind of a meta-level question about whether people should be using the tank story as an example. This one blogger, Warren, he wrote up a very detailed article about this, um, where he tried to look to see if this story actually happened and if there's any real evidence for it. He couldn't find any evidence for it, so he argued that we shouldn't be telling the story because he was saying we should demand high epistemic rigor. And furthermore, he said the tank story he tends to promote complacency and underestimation of machine learning because he argued in reality nobody would be so stupid to let something like that happen. However, the tank story probably was based on real research that happened in the 60s because there is research that was published in the 60s on recognizing tanks in satellite images. And one of the things they do in that research is they specifically correct for brightness levels in the pictures by applying a Laplacian filter. So it's very likely that somewhere along the line someone actually ran into this problem. And I think it is a good story because it really illustrates the problem very clearly. However, there's another story which I think is maybe even better, which is comes from a talk I saw by this guy, Richard Caruana. Oh, Jesse, could you run down for a second? I think someone's coming in, having trouble getting in. So Richard Caruana has a talk where he talks about interpretable machine learning and why it's important. And so he tells a story about some research he was involved in the 1990s where there was an organization called Cost Effective Healthcare that funded a study to see if machine learning could predict the risk of death for patients with pneumonia. And the idea was to use the data on patients to predict the likelihood they were going to die from pneumonia, and then the idea was to take the higher risk patients and have them stay in the hospital longer, and then take the really low risk patients and send them home. Just say, eat some food, drink a lot of water, and call us if you have any problems. Because hospitals are actually a dangerous place to be if you're healthy. So they don't want to keep people there longer than they need to, but they want to keep the high risk people there. So they took the data, they trained up a bunch of models, and it turned out the most accurate model was multitask neural network. And for those of you who know what it is, the classification accuracy had an area under the curve of 0.86. And so they were going to put that model into the field, but they thought it was risky because neural networks are basically a black box. You don't know how they're working exactly. So what they did was they trained up a different machine learning model, which was a rule-based system. A rule-based system was very simple and didn't have the same accuracy as the neural network, but it had the advantage of being highly easy to understand and transparent. So one of the things they learned was the rule-based system had learned that the following association data. If someone has asthma, they are lower risk. And that contradicted the common medical knowledge that people with asthma are generally higher risk. So what they figured out was that what had been happening was the doctors had been taking the patients with asthma, and they had been putting them in the intensive care unit. And therefore, they were getting much more careful treatment, and their risk of dying was a lot lower. So they realized that the neural network had this kind of perverse problem to it, and they decided not to use that in the end. So this is just another example of how the training data can be biased in certain ways, and also example of why being able to interpret models is often important, because in these kind of high stakes situations, especially, you want to know what the model is actually doing, or you want to have some idea of what it's doing, and check with domain experts to make sure what it's doing actually makes sense. And so now I'm going to talk about some other examples of bias, going into the social domain and talking about when the machine learning model is biased and does things that conflict with our values. So Kate Crawford has a talk online now from NIPS where she talks about bias, and she identifies two types of bias. There's bias which causes harms of allocation, and bias which causes harms of representation. So harms of allocation are things which I'm guessing some of you may have heard of. These are situations where there's discrimination in how products and services are given out. For example, a well-known example is, or a well-known area where this can be a problem is in the area of granting mortgages. So by law, you can't discriminate by race, gender, ethnicity, and other protected categories. But but often in practice, due to due to problems in the training data, machine learning models often pick up on race, gender, ethnicity, and other things. Even if it's not explicitly in the training data, it can often kind of infer it. And so people working in those fields, especially where there's a legal obligation or binding legal precedent, they have to be really careful to make sure their machine learning models are not biased in such a way. Other examples you may have heard of are with granting of paroles, which is now they're trying to use machine learning to predict recidivism rates, and then in the insurance industry for determining rates for different people. I'll give another example of that, harms of allocation, but I'm mainly going to talk about harms of representation. Harms of representation are more subtle, and they have to do with sensitive topics like personal identity and group identity. And the harm of it is that you can perpetuate stereotypes or that we don't necessarily want perpetuated. So just as another example of harms of allocation or harms of distribution, I'll there's an example. It was found that in the I believe it was Google Ads or Google Jobs or something like that. They found that women were likely to be shown less likely to be shown ads for high-paying jobs, and I think it was about they were about 8 times less likely. So this is just an example of how like recommender systems could be biased in ways that we don't want. But moving on to harms of representation, a very kind of explicit example of this was when a couple of years ago, Google's photo service misclassified two African American people as gorillas, and I think it's fairly obvious why this occurred. It was probably because most of their training data was on white people. Obviously, they didn't. The training data was not like sampled correctly, or so. This was a pretty embarrassing thing for Google, but there's been a number of embarrassing things that have happened to Google over the years, where they really had to backpedal and scramble to fix them. So this was one issue that came up. Another one was someone figured out if you just type "Jews should" in Google, you start getting all these really racist things. And you know, the fact is, like, the reason these show up is because people actually search for this stuff. So it's accurately portraying what exists in society, but it's portraying things that we don't want to perpetuate forward. You know, another example is that's similar to this is Microsoft had a Twitter bot called Tay. And the idea of that was it was supposed to learn how to speak Twitter language from interacting with people on Twitter. But people started kind of gaming the system and feeding it all this like really racist stuff. And so it became really racist and started tweeting about like neo-Nazi stuff. So they had to shut it down. And similarly, like something like this could also be gamed in theory by people with a certain agenda. So I checked to see if this problem still is there, and it looks like they've fixed it. So I'm going to just go through a few more. Another example is in the ads. There was a researcher at Harvard named LaTanya Sweeney, and she found that if you search for African American names, you're much more likely to see these kind of ads where they're advertising public record searches, and obviously it doesn't look good if the first thing you see when you search your name is was so and so arrested, like check for background checks here, blah blah. And so and the reason this is quite racist is because since the 90s there's certain names which actually are very associated with African Americans in particular. So this is another problem that Google had to fix, and it seems like they fixed it to some extent. Yeah, another problem from Google is in the translator. Um, the translator can be what's found to be sexist because if you say if you have he is a nurse, she is a doctor, and you translate that into Turkish, and then you translate it back into English, it will actually switch, or it used to actually switch uh, the the roles of the job titles. So the reason for this was it was found that so Google Translate uses this type of word embedding called word2vec. Um, and are any of you guys familiar with word embedding? Word embeddings are a way of embedding words into a space where words that have similar meanings are going to be close together. Technically, it's just correlation, so it's words that kind of appear together a lot are going to be close together. But and in reality, these words exist in this high dimensional, 300-dimensional space, but you can project it down to 2 dimensions, and you can visualize kind of how these words are kind of clustered. So what some researchers did was they were able to define a direction in this space, this high-dimensional space, which corresponded to gender. So in one side of this and going in one direction, you end up with words which are more associated with masculinity and the pronoun he. It was actually just based off the pronouns he and she. So going in one direction, you have words that show up associated much more often with the use of the word he. And then going in another direction, you have words that are much more associated with the use of the word she. And so most of these associations are more or less like non-problematic. For instance, boyfriend, girlfriend, actor, actress, things like that. But there are some in here which we would consider quite problematic because they could perpetuate stereotypes and inequalities in society that we don't want perpetuated. So, for example, near she, you find homemaker and feminist. I also highlighted because now you don't have to be a woman to be a feminist. And then on the other side here, you see genius, brilliant, builder, things like that. So these researchers in this paper, they actually came up with a way of debiasing word2vec. So if you're interested in that, you can check it out. And so now I'm going to move on to what Matt was mentioned before, which is the Schenectady problem. So Schenectady problem is an issue that was discovered at Meetup. And one of the data scientists at Meetup discovered that he was analyzing where their users were coming from, how they were distributed, and he found there was a really large number of users in Schenectady, New York. So he looked to see what's going on, and he found right away he saw there was a really abnormal number of users at the zip code 12345, which is an actual zip code in Schenectady, which was awarded to General Electric Research. So some people have reported on this, and they call it the Schenectady problem because it's indicative of a problem often comes in data where when people are asked to fill out a form, they often just put in gibberish or certain 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 patterns that tend to come up. For instance, 1, 2, 3, 4, 5, or 0, 0, 0, 0, 0, things like that. So in data science, you have to be really careful with self-reported data, and you may actually have to throw out a lot of your data if people are just making things up. So moving on, another issue that kind of goes along with cleaning data is normalizing data. So generally, you want to take your data and you want to normalize it so your values, so that the values for different features all fall within a certain range. Because otherwise, what can happen in a lot of models is certain features which have very large values will dominate, and other features that may be really important but have just small numerical values are going to be ignored. So generally, you always want to normalize your data. It also helps speed up the optimization of things like neural networks, because if you think about optimization as like finding the minimum of a function, if your data is not normalized, then the optimization algorithm is going to end up kind of, when it's searching for that minimum, it can end up oscillating and kind of bouncing around in these long valleys. Whereas when you normalize, you have a much nicer surface. It doesn't have those long valleys. So normalization, it is really important. This is also called feature scaling sometimes. But another thing that's not as well, doesn't seem to be as well known, and is sometimes you also have to normalize your target values. So the things you're trying to predict, it's often important to normalize those as well, because again, if they fall over a really large range, there's the same problem where things that just have really high numerical values are going to play a much larger role in the cost function. And your machine learning is going to focus on making good predictions for those things with very large values. Things with small values, it will ignore. So this is just an example from actual work I was doing where I had 3 different models trained on some data, and what I do here is I was plotting the actual value versus the predicted value. So if the machine learning model is working well, then all of these points should just show up along a straight line at 45 degrees. But here, clearly, the model was not working at all. And it almost seemed like in the predictions, it was, for some reason, the model it could just not predict anything greater than a certain number, like 100. I don't know why that is, but what I found was if I normalize the data by taking the log, then retrain the model. So then it started working. So the way you can normalize the target values is either with a log function, um, or some people will use a logistic function, which kind of puts things within a narrow range between like 0 and 1, for instance. But to me, log kind of makes more sense, but I think you could use either one.
Dan, I have a
Yeah.
quick question. Have you ever run into the case where you had negative values and you need to normalize, but a function in that case will not? Well, we're taking this where there are other transformations.
No, but yeah, obviously the log isn't defined for negative values. So you probably have to do something else. Like you could just shift all your data up. You could add a constant and then take the log. I think in practice people use the logistic function a lot. But coming from a physics background, like logs seems to be, kind of makes more sense to me. But yeah, wouldn't work for negative values. So then another thing is not comparing with baselines. So this is also some other actual results from research I was doing where I was trying to predict the heat of formation of molecules. So I had some models that I had trained, and again I was plotting the predicted values versus the actual values and looking to see if they were lining up. And so then I looked at just what would happen if you just took the mean value of the data and you just use that as your prediction. So what that shows is that if you just did something really naive like that, like taking the mean, the error, mean absolute error, was 0.69. You can ignore the units, they're not really correct. And that was actually a lower error than the neural network. So that indicates that the neural network really wasn't useful here, which we sort of already knew, but it was just really clear after comparing with the mean that the neural network was pretty much useless. So I think all machine learning should always, the results should always be referenced to like something simple like taking the mean as a baseline. So, because sometimes people have really, sophisticated models that look really impressive and sound really impressive, but there's often really simple models that do just as well. So again, in the area of like molecules, this has happened a few times where people have trained neural networks to predict some molecular property, and then someone else discovered that there's actually a very simple empirical relationship that describes the data more accurately. So, for example, in one case, someone found that data could be described just by like a 1 over x function, essentially, with one feature variable and just taking the reciprocal of it. And that was basically, in one example, it was more accurate than, for one of the things they were interested in, it was more accurate than a neural network. So another thing you should always look at is linear regression. Um, uh, and that way you can really tell if if it's really worth spending all the time tuning these more sophisticated models like neural networks. A few more things here. So, for example, another pitfall is trying to extrapolate. So, example would be here. This is kind of a silly example, but if we have this sequence 1, 3, 5, 7, you may guess that the next number is 9 because obviously this looks like odd numbers, but really it could be almost anything. For example, it could be 217,341. If you have this particular function, and you're putting in integers as the inputs, the outputs are going to be 1, 3, 5, 7, and then 217,341. So this is kind of a silly example, but it shows you that if you don't really understand what's going on, extrapolation can be really difficult. And generally machine learning is only used for interpolation. So it's only used for finding things kind of between points that you have. I was going to give some more examples, but kind of ran out of time. But this is just showing like how a neural network is classifying some data, and you can see like you can kind of extrapolate it out here, but outside the data, but you don't always know if that's going to be accurate. But for instance, these red points could curve down here. So sometimes you can get lucky, but generally machine learning is not good for extrapolation. So now I'm just going to go on to a little more philosophical point, which asking whether data science is actually a science. And so technically, I think it is a science because data scientists generally follow the scientific method. They collect data. They create a hypothesis, which is the model that they have, and then they look to see if the model fits the data. If the model does not fit the data, they go back and they tweak some of the parameters in the model and check it again. And then they do this over and over again. And eventually they tune all of those parameters so that the model fits the data. And then they test the model further on new data. And so then if the model works, it goes into production, which is kind of analogous to how in science, like if you have a hypothesis that's working over and over again, eventually it becomes a theory. So like parts of science which are really well established and have not been disproven are called theories. So, and then there's a further question of whether machine learning models are falsifiable, because in order for something to be scientific, it needs to be falsifiable. So there needs to be some way of disproving it. And there, I would say they sort of are. Now, I say sort of because the models can be tuned many different ways. But in principle, you can you can come up with data that your model just cannot fit. So these models are falsifiable. So data science, technically it is a science. It is science, but there's a big problem with it, which is that if you're trying to construe it as a science, which is that the machine learning models are bad explanations. So I realized this after watching this talk by this guy, David Deutsch, who's a physicist. And he was talking about the difference between science and things like myths, which also try to explain the world. And he said that the thing that distinguishes science from myths is that scientific explanations cannot easily be changed to accommodate new things. So like if we discover something new, if suddenly we discover something new, you know, generally scientific theories have to be changed a lot. Whereas something like myths, you are very malleable. So, for instance, it used to be thought that like the seasons were due to certain mythical gods and goddesses that were angry at each other, so they every year I can't remember the exact story, but the ancient Greeks had an explanation for seasons where they that David Deutsch talks about, where the spring was the winter came because a certain god was chased out of the region and could no longer heat the earth. But later we discovered that if you go south of the equator, when it's winter here, it's actually summer south of the equator. So his point was that myths could be modified. So you could just say, well, the gods did this or that. But scientific explanations, if they're good explanations, cannot be modified easily. And I feel like it's the same way with machine learning. Like the way you're explaining the data or fitting the data, those models can be modified a lot to fit new data. So they're not like general explanations of data. So another way of looking at all this is basically summed up in this XKCD comic, where they said, this guy is saying, this is your machine learning system. He says, yep, you pour your data into this big pile of linear algebra, and then you collect the answers on the other side. And he asks, well, what if the answers are wrong? Well, then you just stir the pile until they start looking right. And so that's actually kind of how machine learning actually works. You have this very general pile of linear algebra, and you're sort of just mixing it around, trying to get it to fit your data. So I think the meta lesson is, at least for me, is not to be arrogant. I don't like when people are arrogant, for one thing. But here with machine learning, there's all these cool applications. It's great to be excited about those. But a lot of the at least supervised machine learning is basically just curve fitting. John von Neumann had something he said about curve fitting, which is with 4 parameters I can fit an elephant. But with 5 I can make him wiggle his trunk. So with curve fitting you can basically do anything. Okay, so that's it. And